When it comes to wind turbine blade design, in the previous videos we have done on this channel, we have mostly focused on the design of a blade where geometry parameters are already known. But in reality, however, one needs to generate a geometry using the available BEM formulas. There are formulas that can help you to estimate the different angles for twist, angle of relative wind, as well as the angle of attack. You see here in this video, we are going to be focusing on how to generate these geometry parameters for the twist, the angle of attack, the angle of relative wind, based on this formula that has already been uploaded online. So we'll be working with a website to see how to generate this information, and with that you are then able to run the second method of BEM, which is the blade element momentum theory, in order to optimize this wind turbine blade. So there are various steps for wind turbine blade design and construction. You see where after designing a wind turbine blade, it's usually necessary to ensure constructability. For example, if you design a blade where the variation of the twist is too wide, it's often difficult to construct it in the workshop. So the process is now to the ratio of lift to drag actually tells you how far a wind turbine blade can actually be lifted by the air. So if the ratio is low, it means that there's going to be more drag forces effect. So once you have done one of the calculations, one of the methods, you're able to estimate this lift to drag ratio. With that ratio, you are then able to, in a wind tunnel experiment, select different airfoil profiles that can give you that same lift to drag ratio, but on a reduced twist. In other words, instead of you having a twist of 0 at the tip and 30 and 45 degrees at the root, you can have a twist of 0 at the tip and 13 degrees at the root, which is much better, in which case it's easier to fabricate such a wind turbine blade. So you see here we are looking at, so we'll just discuss basically two steps. There are other steps, but we are looking at two steps that are usually used for generating the geometry and optimizing the wind turbine blade geometry and aerodynamics. So one of the approach, method one, is where you select an airfoil. You already know the airfoil you want to use, and you use that airfoil. You use the lift as well as the angle of attack in order to generate the angle of relative wind speed as well as the twists. You'll be able to generate such parameters. Those information, for example, the angle of the twist of a wind turbine blade, when you have the twists, you may not necessarily use the airfoil, but if you have the chord width you can also estimate it from the method one, which we are going to show you in that formula on the website. So once you have the twist as well as the chord width, you are then able to optimize the wind turbine blade for aerodynamics, which is method 2, where estimated geometry parameters are already known. However, optimization of this geometry is performed when you're able to get the induction, you're able to iterate over and get new values of induction as well as angular induction values. So we are only looking at method 1, which is getting the geometry parameters, and we are going to use that in order to evaluate for method 2, which is where you optimize for aerodynamics. So first of all, geometry generation through BEM methods. Then because of the practicality of the twist of the blade, it's difficult to construct such a blade, so you have to use the coefficient of lift and drag ratios in order to find and identify airfoils that meet those same ratio values with less twist. So that's how you're able to achieve your lift to drag ratio without necessarily having a wide range of twists for the wind turbine orientation in terms of the cross section. So a wind tunnel exercise will help you to achieve that. So you can see here we have multiple airfoils, and all of these airfoils, you see you have the cylinder, although in this drawing it looks like an ellipse, but it's actually a circular shape. And you have all the other airfoils. The last image on the bottom right is actually actually it's supposed to show the twist, but not in this case. It just shows it as all of them having the same center of central axis. However, you actually have a twist. So if you had a twist from 0 to 13 degrees and you had a twist from 0 to 45 degrees, you'll see that the variation is wider of 45 degrees and is a little difficult to construct. So this is another image of different airfoils which have been chosen in order to meet after a wind tunnel assessment has been done, be able to identify these airfoils as possible options for the wind turbine. So you can see here this was done in a finite element software whereby we have placed the twist for each of the airfoil cross sections, and you see how the blade is twisting. In this case it's just 13 degrees from the tip to the root. It's just 13 degrees. Imagine if it was 45 degrees. You will see that the variation is much larger. So these are the properties. These are the different parameters that are going to be generated by this method 1 I've just spoken about. So you'll see the blade pitch angle will be generated, the angle of relative wind phi will be generated. So all of these two values are what will be generated. The angle of attack is already obtainable from the calculation that has been inbuilt and based on the airfoil profile. So that's how the calculations will be done. You can always consult literature if you require the actual formulas to estimate the angle of attack and the chord width, and because we're also calculating the chord width here. So you can see this page on the screen. So you can see this image on the screen where it says simple blade calculator. So this simple blade calculator is for method 1, where you are going to calculate the lift. You're going to use parameters of the lift as well as the angle of attack in order to estimate the angle of relative wind, the twist, as well as the final the chord width and a few other parameters. So you see here, these cells are the cells that need to be filled. So for example, starting from the top left, you have blade radius. You can always edit this and place your own blade radius. Number of blades, here is 3. You can always edit for what you want. Rated wind speed. So what's the rated wind speed of the wind turbine? Is it 11 meters per second, 12 meters per second? What is it? Then the tip speed ratio, you need to know that value as well. Then if you come here, you can actually select the profile name. Under profile data, the first column we're looking at was basic information. Now we are looking at profile data. Under profile data, you can actually select any of the airfoils that you require to analyze. This is a simple approach. So you can select one of the available profiles here in order to carry out your calculations. Then you'll be able to select the angle of attack at this optimum coefficient of lift value, as well as the maximum lift to drag ratio. I spoke about this. This shows you how much the wind turbine blade is able to lift. The higher this ratio, the more freedom the wind turbine blade is going to move in the air. So you have hub radius, the root width. So all of these are geometric parameters of the wind turbine blade, which are usually provided by the manufacturer. Then number of stations, so the number of point divisions along the wind turbine blade. So you can make it 20 if you want more divisions, but 10 is fine. So that's it. So the other a linear approximated blade is very much easier to make and is surprisingly closer to the ideal blade shape in terms of performance. The best points to choose are usually between 0.5 and 0.6 for the first point, and between 0.9 to 1 for the second. All of these have already been imputed, so there is no need to make any adjustments to it. So if you then scroll down, you have other parameters. So if you click on calculate, it gives you a calculation. So let's say we change parameters to, let's say the radius is 493, 4930. So for that 1000 millimeter radius, you can see here the parameters that were estimated. So if you remember these numbers, you see here, if you remember these numbers, you'll be able to know the difference between what is here as the demo and what you calculate based on your own value. So let's say we are using a lift and drag. Let's say we are using a lift to drag ratio of 57.209 is fine. Let's say we are using a wind speed of 12 meters per second. Let's say we change the airfoil. We have to change the angle of attack value, the coefficient of lift, and all the other parameters. So let's use NACA 4421. So what do we see here? First of all, before we click on calculate, at the bottommost right of this table, you have minus 83.5 millimeters. Okay, let's say the chord. Under using linear approximation, under chord column, you have 153 millimeters. That's close to the root. That's the chord width. So let's say we then run this calculation. After running the calculation, you see here that the chord width close to the root is around 813 millimeters, which is much more than what was there before. So this is how the values are graduated. So for an ideal blade, these are the parameters you get. But when you have using linear approximation, which gives you a better estimate, you can see here angle of attack. Under the column of angle of attack, you have from 5.5 degrees at the tip of the wind turbine blade to 37.8 degrees. So if you look at this formula here, we'll be working with this formula. So you see here, angle of relative wind speed is the blade pitch plus the angle of attack. So we are going to look at the angle of relative wind. So angle of relative wind is angle of attack plus the pitch, right? So you can see angle of attack as 5.5. So angle of attack plus setting will give you adjusted set. So the adjusted ADJ set is the angle of the relative wind, while setting is actually the pitch angle. Attack is the angle of attack. So angle of attack plus pitch angle or setting will give you the angle of relative wind speed. So you can see apparent wind, you can see the values which were calculated. So the adjusted set is showing you that there was some error. So the correct values is what has been provided in green under adjusted set for the angle of relative wind speed. So that's basically how you can use this application in order to calculate the geometry, the twist of a wind turbine blade cross section when you know the airfoil you want to use. And once you've selected that airfoil and optimized it, you are then able to switch it with other airfoils and use method 2, in which case you are optimizing for the angle, the lift and the drag. Once you optimize the aerodynamics for lift and drag, you are then able to use a wind tunnel assessment in order to find airfoils that result in twists that are not too large, that will make it easier to construct such a wind turbine blade cross section. Thank you for watching this video. This is Catchment of Resources, where we create for better living.